Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on vectors. Now in previous videos we've talked about how to multiply two vectors together, we've talked about dot products, cross products and scalar triple products. And in this presentation I'm going to continue using these special forms of multiplication to talk about an equation of a plane, and in particular the PointNormal form of the equation of a plane. So I'm going to discuss that. I'm going to talk about the geometry behind it, and I'm going to discuss an example. So let me share my screen with you and I can show you what I mean. Okay, so up until now we've seen two kinds of equations for planes. There's the Cartesian form where A, B, C and D are constants, okay, and real numbers. And there's also the parametric vector form, which is in the following format. Okay, so here A is the position vector of a point on the plane, lambda1 and lambda2 are the parameters, and v1 and v2 are vectors that are parallel to the plane. So this is like the parametric vector form. Okay, so now it's time to discuss a third equation of a plane called the PointNormal form. Okay, so let me just draw a little picture and it will motivate this expression. Okay, so let's say I've got my plane here, right? And I have a point, say, on the plane, and I know a vector that is normal to the plane. Okay, well, for every point x in that plane, I can form a vector from the known point A to the vector to the point x, and this angle between the two vectors, normal vector and the vector lying in the plane, must be the two vectors must be orthogonal, normal, or perpendicular. So that angle is like 90 degrees or pi on 2 radians. Okay, now when we discuss the dot product, we know that two vectors are orthogonal, perpendicular, or normal to each other when the dot product of the two vectors is 0. Okay, so if I just sort of draw in an origin here, then really this is the position vector of x, and this is the position vector of A. So the vector AX is pretty easy to calculate, okay? Right, so just by the triangle law of addition, the vector AX is just the position vector of X minus the position vector of A. Oops, sorry, I put in a hat there, that shouldn't be a hat. Okay, so it's just the position vector of X minus the position vector of A, and so we get this. Okay. So star arises. Okay. All right. Well, let me give you a quick example of this PointNormal form. And I'll do a more structured example in a minute. But let's say the normal vector is, say, the vector 1, 2, 3. and say A is the point -1 to 4, a point on the plane, and the notation that we use for this vector in, say, three-dimensional space is just the column vector x, y, z. So for these, this information or this data, the point normal form of the plane associated with this information is the following. Okay, so this will be 1, 2, 3, x minus a. So it's that minus -1, so that'll be x plus 1, that minus 2, that minus 4. Now, so that's essentially the point normal form of the equation of the plane associated with this sort of data. Now, it's easy to go from this to get the Cartesian form. All you would do is expand out this dot product and simplify, okay? So this can be converted to Cartesian form by evaluating the dot product. Okay, so what I'm going to get? I'm going to get 0 equals 1 times x plus 1. See if I can squash it in here. Plus 2 times all of y minus 2 plus 3. Okay, that's a 3, that's a z. I know they look alike. Times z minus 4. Okay, so I'm going to get x plus 2y plus 3z. And then the constant's 1 minus 4 minus 12. Okay, so I'm going to get -15. All right, so take the 15 to the other side, and you have got a Cartesian form for this. Okay, so let's do an example here. One of the nice things about this vector is this form is that it sort of gives you some geometry with the problem. And you may be thinking, okay, what happens if I start with, say, a Cartesian form? How do I get back to here? Well, it's pretty easy. It turns out, I'm not going to show this, that the coefficients of the variables, the a, the b, the c, are the components of a normal vector to the plane. Okay, so you would sort of start with this, you would go back to this form, and it's pretty easy to work out a point on the plane from this equation. Just let x, y, and z equals 0. X and y equals 0, then z's got to be d on c. So you can kind of work backwards. All right, let's do the more formal example here. Consider a parametric vector form for a plane calligraphic P. Does this given point E lie on the plane, and why not? Okay. So what I'm going to do here, you can do this question a number of ways, but I'm going to do it using the point normal form. And what I'm going to do is try to convert this from a parametric vector form to the point normal form, and then I will actually test the point normal form to see if sorry, that was the wrong page, to see if this thing holds. Okay, so let me show you. So what do we need? We need a normal vector and a point A on the plane. All right, so the point associated with this position vector lies on our plane. Now, this vector and this vector are both, say, parallel to the plane. And I know from our talk about the cross product, I can form a normal vector to both of these vectors just by computing the cross product of, say, V1 cross V2. Okay, that means that this vector is going to be normal to both of these vectors and therefore the plane that they're parallel to. Okay, so a normal vector 2p can be calculated via the cross product. Okay, so in this setting, the normal vector is going to be the cross product of v1 and v2. Now we know with the cross product that we can evaluate it using a determinant type algorithm, right? So you put your ijk, your unit basis vectors up here, and then you write this as the v1 as the second row and v2 as the third row. And our answer will be a vector. Okay, so with a 3x3 determinant, you start up here and you work your way across the top row. So you cover up, the first step is to cover up the row and column that i's in and multiply by the determinant of what's left. Oh. Okay, so it's going to be 3, -2, 2, -4. Okay, move on to the j. Cover up the column and the row that j is in, and you multiply j by the determinant of what's left. Okay, now you want to go to a minus sign here. With determinants, when you go positive, negative, positive, negative, positive, negative along the top row. Okay, 1, -2, 3, -4, and let's see if I can squish the last one in. So k is in that row and that column, so multiply k by the determinant of what's left. Okay, just squeeze it in. Okay, so with these 2x2 determinants, you work diagonally. That times that minus that times that. That times that minus that times that. That times that minus that times that. Okay, so I'm going to get negative. I've left off the minus sign. Okay, I've just left off the minus sign when I moved that over. Okay, so I'm going to get -3 times -4 minus -2 times 2. So that's going to give me 12 plus 4. Okay, so over here I've got -4 minus -6. So the determinant is going to give me a +2, and I'm going to have the negative from the front. And over here, I've got 1 times 2 minus -3 times 9. So that's 2 plus 9. So that'll be 11k. All right, so I can, if I want to write that as a column, I can write it like this. Okay, we have got a point on the plane. We've got a vector that's normal to the plane. Now we can put the point normal form together. Okay, so it's 0 equals n dotted with x minus a. So in this case, it's this vector here, dotted with, okay, so the position vector is just there associated with that point. So x minus 5, y minus 0, z minus 1. Okay, we still haven't answered the question though yet. Okay, so what we want to do is test whether or not this point satisfies this point normal form. Okay, does this equation hold for x equals 3, y equals 0, and z equals -1? If it does balance and hold, then E will lie on the plane. If it doesn't hold, E will not lie on the plane. Okay, so So let's consider this thing here. 16, -2, 11. All right, let's plug in. So 3 minus 5 will give me -2. Y equals 0 will give me 0. And -1 minus 1 will give me -2. Okay, so to evaluate this dot product, you multiply component y by component wise, and you add up. Right, so we're trying to see if this equals 0 or not. So we're going to get -32 plus 0 minus 22. Okay, it's obviously not going to be 0. Okay, so let's make a conclusion. Hence, star does not hold, and so E cannot lie on our plane. Okay? All right, so that's the end of the example. But let me go back to what I said before about how to produce a normal vector. Now, when you're given the say a parametric vector form, it's easy to produce a normal vector. You just take the two vectors v1 and v2 and cross them together. If you're given a Cartesian form, okay, I claimed before that you can just take the coefficients of x, y, and z, write them as a vector, and that's a normal vector. So something for you to think about. How would you actually show or prove that that method actually works? That if I think of the vector A, B, C, that really is a normal vector to the plane associated with that. Well, I'll leave you to think about that. If you have any questions or suggestions, put them in the comments section. Okay, so that's my presentation on the PointNormal form for the equation of a plane. Thanks for watching, and in the next video I'll be talking about distances between, minimum distances between points and planes. So I hope you can join me. I look forward to your company then. If you have any questions, any comments, put them in the comment section. Any suggestions, I'm always really interested in feedback. So thanks for watching. Hope you can join me again. Bye.